Good day, everyone! How are you? This is Teacher Rachel, and I'm here today to discuss to you about the ideal gas loss. Before we start, here are some reminders. First, observe safety protocols. If you are with your friends and sharing the same laptop or Wi-Fi, please observe social distancing. Wear your face mask properly and make sure alcohol is always with you. Second, answer the activities given to you. The first activity is about exploration and the second one is checking comprehension. Last time, I asked you to download the app Kahoot. I hope you already have an account on the app because we will be using it in our lesson for today. Here are the mechanics of the first activity. First, enter the link on your browser. The link will be posted later. You will be asked to log in your email and password in Kahoot. Once logged in, you click on the play button. Then, click practice. Second, enter your name using this format. Family name, comma, first letter of your first name. Then, click the OK button. Answer the questions individually using the Kahoot app in 5 minutes. You will be able to see your scores after answering. The faster you answer, the higher your scores will be. And to make it more challenging, we will be tallying your scores and add them with your group mates. So, who will be your group mates? You will be grouped alphabetically. Send the screenshots of your total scores to me, and after tallying your scores, the group with the highest score will receive a prize. The prize will be It's a Surprise. Please copy and paste this URL in order to open the Kahoot.id. Are you now ready? Your 5 minutes starts now. Good luck! has neither definite shape nor volume but tends to expand indefinitely. If we make a couple simplifying assumptions about gases, we can make some easy predictions. Number 1. Particles in a gas are dimensionless points in random motion, and the identity of a gas is irrelevant. Could be any. Second, the particles don't interact, apart from elastic collisions bouncing off one another like balls on a pool table. These things are not completely true, but they make the math easy and surprisingly accurate. So these kind of gases are called ideal gases. So what is an ideal gas? Ideal gas is essentially point masses in moving constant, random, straight-line motion. Its behavior is described by the assumptions listed in the kinetic molecular theory of gases, which was discussed last time. When examining an ideal gas, we want to be able to discuss 4 variables. First, pressure. It is defined as the force the gas is exerting on the container. Second, the temperature. Temperature is the amount of heat energy available to be able to transfer into kinetic energy of motion. The higher the temperature, the faster the particles move. Third is volume. It measures how big the container. Moles. How many particles are there in the container? To sum it up, how many particles, how big is the container, how fast do particles move, how often do they hit the sides. These variables are dependent on one another in interesting ways that have been formulated into laws. Let's look at a piston. While keeping the moles and temperature the same, in other words, the same number of particles moving at the same speed. If we must compress the volume, the pressure must go up. The particles will be hitting sides more often because there is less distance to travel to hit a side. That means that pressure and volume are inversely proportional, meaning when one goes up, the other must go down. And this is expressed in Boyle's law. P1V1 is equal to P2V2. If we double one variable, we must cut the other one in half in order to keep this equation valid. Volume and temperature is also related. If we have a gas in a balloon and we heat it up, the particles will move more quickly in order to keep pressure constant. The volume will have to expand, which means that volume and temperature are directly proportional. If one doubles, the other must double. And this is expressed in Charles' law. When we do calculations with temperature, we must always use an absolute temperature scale called the Kelvin scale. 1 degree Kelvin is the same magnitude as 1 degree Celsius. But 0 Kelvin is absolute zero, the lowest temperature possible, a complete absence of heat energy, which is negative 273 degrees Celsius. In order to convert Celsius to Kelvin, simply add 273 and to do the reverse, subtract 273. The combined gas law is the combination of Boyle's and Charles' law, which states that the ratio of the product of pressure and volume and absolute temperature of a gas is equal to constant. Avogadro's law says that equal volume of gas at the same temperature and pressure contain the same amount of molecules, specifically that 1 mole of ideal gas occupies 22.4 liters at the standard temperature pressure, regardless of the identity of the gas. Lastly, when Avogadro's law is added to the combined gas law, all variables correlate in one equation called the ideal gas law. This also contains the gas constant R. There are different values depending on the units used for this constant variable, and we will be using this one. This equation is useful when we are not looking at a change, but just to know the value of all the 4 variables at once. So if you're looking at a sample of gas and you have 3 of the 4 variables, then you can solve the fourth using the ideal gas law. If you are given some initial conditions as well as some final conditions, you can use one of the other laws to find the unknown. There's no need to memorize all the gas law equations. All you need to remember is the formula PV is equal to nRT. And this simple technique will help you derive the equations for every missing variable. Simply cover the unknown. Just plug in what you know and solve for what you don't.
Attention please. Attention please.
Let's check comprehension. Enter the link and you will be directed to the Google Classroom. Good luck!